All right. So first thing I'd want to do here is begin drawing out my tree. When you're looking at bags at the airport that are going through security, is the first thing that would happen whether or not someone decided to pack something forbidden to go on the airplane? Or is the first thing that would occur the alarm going off? Person packing ahead of time. Whether they knew it was forbidden or not, the person actually had to put the item in there first. The detectors at the airport are there to set off an alarm if it finds something that's already there. So when I go to do my tree diagram, my first branches are going to be whether or not it contains something that is forbidden. I would have forbidden, and not forbidden, or forbidden complement. What does it tell us the probability is that somebody decided to pack something forbidden? 5%, so 0.05. So what's the probability that somebody did not pack something forbidden? 0.95, yes, 95%. Whether or not they decided to pack something that's forbidden, everybody's got to send their bags through the security, right? All right, so then what are the possible things that can happen when you send your bag through security? Sets off an alarm or it doesn't. Alarm or no alarm. And it has to go through this screening process where it either does or does not set off the alarm, whether you packed something forbidden or not. So alarm or no alarm are options off of both of these. Here's where our conditional probability comes in. If we're up here, if somebody decided to pack something forbidden, what's the chance that it sets the alarm off? 98%. So up here, 0.98, that if it really contains a forbidden item, so I'm up here, it sets the alarm off 98% of the time. What's the chance then that somebody packed something that was not allowed and it didn't set off the alarm? 0.02, 2%. Nothing's perfect. It catches most of them, certainly catches far more than half, right? And some things can sneak through. Anybody been to the airport recently? Anybody get their bags flagged for an extra check? I did. When I went to Disney with the orchestra, especially when we were going not necessarily through the airport, but through the Disney scanners, you'd walk through the metal detectors and everybody that was fine, you can go ahead and go in. Almost every single day, I was in the, no ma'am, you have to step over here. We have to check your bag. I didn't have anything forbidden, but I had something that was setting off their alarm. So they had to go through my bag and check to make sure that it wasn't actually one of the forbidden items. What's the chance that it doesn't contain a forbidden item, but it still triggers the alarm? 8%. In my case, it was an external battery that I brought in case my phone died. It kept kicking off their alarms. The smaller ones weren't, but I had like a big heavy duty one so that I could charge anybody's phone. And that was kicking it off because it was showing up as this strange, large, square metal object. And they're like, what do you have in there? Not forbidden and does not set off the alarm. What's the probability there? 92. I finally figured out on the last day in the parks what it was, and I held it out in front of me when I went through their scanners. And that was the only day that they let me go right in. Like, I knew that's what it was and figure it out till the last day, but. All right, so now I want to calculate all 4 of these probabilities. Somebody packed something forbidden and it set off the alarm. How do I calculate the probability that they had something forbidden and it set off the alarm? Multiply. So we're going to multiply 0.05 with 0.98. We're going to do that for all 4 of these. So grab your calculator so that you can do that. What is it for? You have a forbidden item and it sets off the alarm. What do we get there? 0.049. This again is the probability that you have something forbidden and it sets off the alarm. Oh, sorry, I wrote that in the wrong spot. My apologies. Let me get it in the right spot. It should be up at the top. .049 probability of forbidden and sets off the alarm. You packed something forbidden and you got away with it. 0.001. The probability of forbidden, and instead of no alarm, I'm going to call this alarm complement. That would be the opposite of setting off the alarm. You didn't pack something forbidden, but you set off the alarm anyway. 0.076 probability of forbidden complement and alarm. And finally, you didn't do anything wrong and your day went smoothly. You didn't pack anything forbidden and you did not set off the alarm. 0.874 probability of forbidden complement and alarm complement. And all of those blue probabilities, the ones at the end, those should all add up to what? Should all add up to 1. Double check. If you've had to round anything, sometimes it adds up to 0.99999, and you know that it's just the rounding, and that's the only reason that it's not adding up to that whole number of 1. They asked us, given that a randomly chosen bag triggers the alarm. Before I even read the rest of the question, if it triggered the alarm, which ones of these am I possibly looking at? First and third one. This one set off the alarm. This one set off the alarm. Given that it sets off the alarm, what's the probability that it contained a forbidden item? So the probability of forbidden given that it triggered the alarm. The way we calculate this probability, it's going to be a fraction. We're going to do some dividing. What do I want up on the top of my fraction? The probability of forbidden and the alarm. What do we know happened in this circumstance? The alarm was triggered. So my denominator is the probability that the alarm went off. How many different ways could the alarm be triggered according to our tree diagram? 2 different ways. It gets triggered if you did pack something forbidden. Sometimes it gets triggered if you didn't pack something forbidden. But both of those probabilities have to go into my denominator. So on the bottom, the probability that the alarm went off, what happens when I add those two together? 0.049 plus 0.076. What do I get when I add those two together? 0.125. I don't know how good anybody is with their decimal to fraction conversion, but that's 1/8. So 1 out of every 8 bags is setting off this alarm. Just from having been to the airport, having been to places where they have security, does that mean 1 out of every 8 people on average is trying to get something in here that they shouldn't? No. But the screening devices that they have are only so sensitive. That's why they have people go through it, but they don't have time to have people check every single bag. What should go up in my numerator? 0.049. Those are the ones that set off the alarm because they contained a forbidden item. Pop that fraction into your calculator and tell me what that would be. 0.392. What does that mean? What did we just find? Yeah. So thinking about those lines that they make you go to when they're like, we're going to have to check this by hand. About 39% of the time, they're actually recovering forbidden items. The other about 60% of the time, 61% of the time, it's something else that set it off. So there's more innocent people in that line than guilty people, but they're catching 98% of the people that are trying to get forbidden items in there. Does that make sense? All right. I want you guys to flip this over. There's a very similar problem on the back, and I mostly want you to try it on your own. The only thing I want to ask you is which event here would have to happen first? What are the two events that we're thinking about here? Having a disease or not having it, that's one event. What's the other event? Testing for it and either coming up positive or negative. Which one of those things would happen first? You either take the test and then get the disease, or you get the disease and then test for it. Get the disease or don't. You're showing symptoms, you think you might have this. So the first branch should be whether or not you have this disease. The second set of branches should be whether those tests come out positive or negative. I want to give you guys let's take about 3 minutes, and then I'll go through how to do this to make sure that you're coming up with the correct probabilities. Almost identical to the front side. Probability you have the disease? What was the probability that you have the disease? 0.1 or 10%. 0.1. So what proportion of the population does not have the disease? 0.9, 90%. If you have the disease and you take the test, what's the probability that it popped a positive? 99%, 0.99. So what's the chance that the test failed you and you slipped through the cracks? You really are sick, you're contagious. The test told you you were not. 0.01. You don't have the disease, but it still popped a positive. 0.05. You don't have the disease and you got a negative. 0.95. All right, so we're going to multiply along our branches to find these probabilities, and then I want to make sure that we know what we've just found the probabilities of. So I've got 0.10 times 0.99, which gives me what? 0.001 or 0.0099 when I did it on my calculator. 10% times 0.01. What would that one be? Yes, 0.001. Down at the bottom, I've got 0.90 times 0.05. And we get what? .045. And finally, we take 0.90 times 0.95 and get what? 0.855. Tell me what these are the probabilities of. What does this 0.099 represent? They had the disease and they tested positive. So this one right here is the probability that they have the disease and they are positive. So what's this 0.001 then? They have the disease, but they tested negative. What's this 0.045? They don't have the disease, so disease complement, and they tested positive. 0.855. No disease, and it came out negative. All right, so to answer the question that they were given at the beginning, or that we were given at the beginning, if a random patient tests positive, where am I looking for that? .099 and 0.045, because these have people that tested positive. Are there any other ends of these branches, any other leaves where it's showing a positive test? Nope, the ones that I left out are for negative tests. So given that they fit in one of these two categories, I want to know what's the probability that they have the disease. What does my probability notation look like as I write this down? Because it's really important for making sure I get the right fraction. Disease, given that you have a positive test. So this is going to be a fraction. What goes up on the top of that fraction? Disease and positive, which is what according to our tree diagram? 0.099. What goes on the bottom of my fraction? All of the positive tests. So how many n's did I have with positive results? 2. I have to add those together to figure out the probability of a positive. 0.099 plus 0.045. What do I get when I add those two together on the bottom? 0. You said 144? And I've got 0.099 up on the top. When I divide those, what do I get? 0.687. So what does that number mean? That's exactly correct. If somebody tests positive on this test, sitting at about almost a 69% chance that they really do have this disease. False positives are a thing, but this is catching most. Yes, ma'am. To the best of my understanding, and if I find out different information, I will clarify, but to the best of my understanding, if they ask this question, if a random patient tests positive, what's the probability that they have the disease? You could leave it just like this. I just want to make sure for our own understanding in here that we know what that value is representing. So that's why I'm constantly like trying to put it back into the context, because we have no way of climbing inside somebody's biology and saying, do you really have this disease? All we have is this physical evidence of a positive or a negative test. We know that some people are slipping through the cracks. Some people have the disease and they don't know it, even though they've tested. And some people don't have the disease, but that test is still popping up positive for whatever reason. Maybe there's another medication that they take that is causing this false positive. But almost 69% of the people that test positive really are ill individuals with this disease. All right. On your review, I do want to take questions, but I also wanted to make sure that we had a chance to talk about some of the ones at the end that are short answer, so that we have a chance to go through some of those. So I wanted to start all the way at the end with number 20. The first part of this question should look kind of familiar. Why? Homework. Yes. Homework asked you to draw a tree diagram to explain this. We want to find the probability that a student has a parking pass. You can absolutely do this with a tree like we just did. Since the school is awarding parking passes based on these percentages here, Do you think the first thing the school does is hand you a parking pass, or the first thing they do is look up what grade you're in? Grade. So if I'm making a tree diagram for this, grade is the first thing I'm going to do. How many branches are we going to have? 4 technically. I don't have to have a freshman branch because do they ever get parking passes? No, but there's nothing wrong with including that 4th branch so that we can see all those pieces. So I could do freshman, sophomore, junior, senior, something like this. Sorry, I'm going to make that a little bit better. What proportion of the school is freshmen? Says in a large high school, 24% of the students are sophomores, 26% are juniors, 30% are seniors. 20%. Tell me how you got that. Subtracted from 100%. So if I add all these up, that'd be 50, 60, 70, 80% right there. So I know 20% has to be freshmen. For the other ones, my numbers aren't too bad. I can just pull those right from here. 0.24, 0.26, and 0.30. Then we've got our next set of branches. What are the next set of branches? Parking pass or not? So I'm going to do PP for parking pass and PP complement. Freshmen that get a parking pass, 0. So freshmen that don't get a parking pass, 100%, or I could put that as just a 1. Sophomores that get a parking pass, 15, so 0.15. Sophomores that don't, 0.85. Juniors that do, 0.25. Juniors that don't, 0.75. I'm switching colors so that hopefully you can tell which numbers go with which branches. Seniors that do, 0.55. Seniors that don't, 0.45. I don't really want to calculate all 8 of these probabilities. What are the ones that we're interested in? Because I'll put a star next to them. Parking pass. So this is a parking pass, this is a parking pass, this is a parking pass, and this is a parking pass. So now I only need to calculate 4 things. I'm going to multiply along all of those, and then I'm going to add up the results. So I have 0.20 times 0. I have 0.24 times 0.15. I have 0.30 times 0.25. Or sorry, not 30, 26. I was looking at the wrong spot. I apologize. 0.26. And then 0.30 times 0.55. And then once I get all of these, I will add them. This is just like when we were finding the denominator before. 0.24 times 0.15 would be you said 0.03336. Thank you. 0.26 times 0.25. 0.065 and 0.30 times 0.55. 0.165. Is that right? Oh, 0. I wrote it down wrong. You said it right. I wrote it down wrong. There we go. And then we add those 4 up. Since freshmen don't get any parking passes, they don't contribute anything here. So I get a 0. 0.266. So the probability that somebody has a parking pass is 0.266. Lots of P's there. You can write it out, but it's very standard in probabilities to abbreviate what you're putting inside those parentheses. If you're afraid it's going to be confusing like this, where it's P of PP, you could say, I'm going to let event A be a student has a parking pass. And then I would say probability of A. Suppose the chosen person does not have a parking pass. What's the probability that he or she is a junior? How would I calculate this? What does my probability notation look like? Let's start there. Probability of being a junior. This is the thing that we want to know the probability for. What do we know about them? They do not have a parking pass. So the first thing I want, what would I have in my numerator then? Junior and no parking pass. Down in the bottom, I want what? Look back at that other worksheet that we did. What was going down in my denominator? No parking pass. Whatever they tell me, suppose this thing or given this thing, those are the ones that I'm looking at. So probability of no parking pass. Whatever comes after this is what goes on the bottom. So did we calculate these numbers? No. Yes, sir.
You said whatever comes after the given goes in the denominator?
Yes. Whatever they're telling us to suppose, whatever they've given us, whatever I have after the given that symbol, that's what goes down in my denominator. How can I find junior and no parking pass? Where would that go? Junior and no parking pass. Look at the tree. What do I want to multiply together to figure this out? 0.75 times 0.26. 26% are juniors. 75% of them do not have parking passes. So I didn't calculate it from my tree, but it would be this piece right here. Do I have the probability of no parking pass? I can find it though, can't I? I have the probability that they do have a parking pass. So how do I find the probability that they don't? Yes, subtract it from 1. It's going to be 1 minus the probability that they have a parking pass, or 1 minus 0.266. What do I get when I multiply the numerator part together? 0.195. And in that denominator, I have 1 minus 0.266, which is 0.734. Divide those on my calculator and we get what? So if I have everybody that does not have a parking pass, please report to the East Gym. Everybody from the entire school that doesn't have a parking pass goes down there. As they go in, I hand them all raffle tickets and I pull one. This is the chance that I picked a junior out of all the people with no parking passes. Does that make sense? Okay. There was another part to this question that has this table down here, or not table, dot plot. What's the claim? Out of the 40 seniors in the AP Stats class, only 10 have parking passes. So what do they think about that? They're thinking that maybe they're being discriminated against. Are you guys on purpose picking on us just because we're taking AP Stats? Because they know that 55% of the senior class is supposed to have parking passes, right? So ballpark, how many would you expect in a class of 40 should have a parking pass if it's all seniors? Yeah, 20, a little bit, like hovering a little bit higher than 20, right? But if it was half the class, would you be surprised? No, this is only a quarter of the class. So they're a little taken aback by this information. What's the probability that this is just by chance? That of these 40, we just managed to get more of the nots than the do's, more of the no parking passes than the do have a parking pass. This is where simulation comes in. So they had simulations from a population where 55% had parking passes. So like I have a jar of 100 marbles and 50 of them have the letter P written on them. And I mix them all up and I draw out 40 marbles and I record how many of them have parking passes, how many of them have a P on it. And I put a dot. Put all the marbles back in the jar, mix them around, pull out another sample of 40, and I record how many of them have P's on them. This dot plot is running that simulation 60 times. Of those 60 simulations, how many times did 10 or fewer parking passes show up? 9 times. So right here, this is 10 or fewer parking passes. In a simulation that's supposed to represent this school, 55% of our seniors had a P on their marble for a parking pass. We drew out groups of 40. 1, 2, 3, 4, 5, 6, 7, 8, 9. Out of, how many times did they run this simulation? 60. What is that as a decimal? 9 out of 60, you said 0.15? Is the school discriminated against them? I mean, we don't know for certain, but I can make a pretty good guess at this point. How am I using this to make a pretty good guess that the school is not actively discriminating against these group of kids? 0.5 is my cutoff. If this came out to be like 0.04, sorry, not 0.5, 0.05, 5% is my cutoff. If this came out to be 0.04, then the chance that this group of kids in the room would have just randomly occurred, where only 10 of them have parking passes. This isn't happening very often just by chance. 15% of the time it showed up just by chance. So we do not have convincing evidence. I would say having a class of 40 students, 40 seniors, sorry, seniors, where only 10 have parking passes. Occurred 15% of the time in a simulation. This is not rare. So we do not have convincing evidence. The school is being unfair to AP Stat students. Right. Looking back at previous problems, 18 and 19, that extra page that we did together are very helpful for 18 and 19. Think about the way I described how this simulation was come up with, or one possible way that that dot plot was made. You guys, one of the questions on your review is to describe how you would design a simulation. Please make sure that you know how to do that. Get in touch with me over the weekend if you have any questions. I will post all the remainder of the answers on Canvas by the end of the day today. Have a fantastic rest of your day, guys. Have a good weekend, and I'll see you on Monday for your test. Yes.